Okay, well, good evening, everyone. Thank you all for joining, and it's been lovely to speak with some of you just prior to the start of the talk now. Absolutely great to have people from such a wide geography. We normally only get an audience from Essex or mostly Chelmsford because of where we're based, but doing it online seems to have brought in a wider crowd, which is fantastic. So thank you all for joining, and for please do continue to post where you're from in the chat. Some people have been doing that. We'll keep a record of that so we can just reflect on that later. So thank you. Just a few things before we start. As I was saying earlier, I've muted everyone for the duration of the talk, just so we don't get any unwanted interruptions. If you have any questions for Alan throughout his talk, please just post them in the chat. There's a chat facility button at the bottom of your screen, and you can type in there. Make sure the message goes to everyone, not to a private person, as it can sometimes do. And then I will pick up those questions at the end of the session and pose them to Alan. And then if anybody has any other questions throughout that, we can open up the microphone and people can ask them live, as it were. So that's the kind of the proceedings. So this is a Chelmsford Science and Engineering Society talk, although it's co-presented with Marconi Heritage Group, Chelmsford Civic Society and various other organisations. It's all part of Essex 2020, and this specific talk is part of a series of centenary lectures that CSES is putting on to celebrate its centenary year this year, 2020. You can find out more on our website, cses.org.uk, or chelmsfordses.org.uk, but both work. And I would encourage you to have a look on there and see what other talks are coming. There's another one from Tim Wander next week. We had one from him last week. The video of that is available. Also, the video of his play, which was live streamed from the theatre last night to coincide with the exact centenary of the Nellie Melba broadcast, is available through our website on YouTube. I've been advised by Chris that a cleaner version of that is currently being edited and prepared for release, because there were problems with the bandwidth on the live stream. So please do have a look at the other events, see what takes your fancy. Anyone's welcome to join. And of course, if you feel like joining the society, it's a very reasonable £12 or free if you're involved in education in some way. Annually, and that gets you can get regular updates by email of what we're doing, and access to the video archive, which goes back further than the last few months. So that's enough from me. So I'm delighted to be able to introduce Alan Hartley-Smith this evening. We're privileged to have him with us and able to give us this talk this evening. Alan, he may want to provide a little further background, but I'll give you the brief summary. So Alan, it's fair to say, has done the rounds of the science and technology companies in Essex. So he originally served in the RAF and then joined Marconi at the Baddow Research Laboratory, which I'm sure many of you will be familiar with, working in radar and various things. Then he moved to STL, Standard Telecommunications Laboratories in Harlow, then to Ferranti, and then which became Plessey, and then to UMIST. So quite a varied and illuminated career. So yeah, we're privileged to have Alan with us this evening, and he's going to talk to us about the development of computing within the Marconi company, which is a side that I suspect people are less familiar with. It's less famous than the radar and the radio aspects, which of course there are other events going on at the moment to celebrate. But this is an absolutely crucial part of our history and of the history of the world, really. So Alan's going to open our eyes to that, I think, and we'll all learn something. I think that's the main thing. So that's it for me. I'll hand it over to Alan. Thank you.
Oh, first, good evening, everybody. Nice to have a good audience to talk to. I do like audiences. So what I'm going to try and do tonight is to illuminate people with regard to Marconi working in computers. because we didn't really get much in the way of exposure in terms of being a British manufacturer. Many people don't even know that Marconi made computers. So hopefully after tonight, there will be a few more. First, we are, of course, part of the Marconi Story, as just been said. The Essex 2020 series is going on. Tim has covered the wireless communications and mentioned the developments throughout the First World War. Last night, we had the play introducing radio broadcasting. And of course, later in the years, that was produced television and principal applications in the domestic market in the lead up to the Second World War. And of course, that started us out on radar. And there was the period after the Second World War. So I'll be covering those consecutively. What I'm going to do is base the thing, and I think it's rather neat. Earlier this year, James Lovelock, a very respected scientist philosopher, produced a new book called Novacene, The Coming Age of Hyperintelligence. And he's talking about this planetary age of artificial intelligence and thinking machines, very appropriate. He says there was a previous period called the Anthropocene, and this really was the start of the Industrial Revolution. But it's very interesting that right at the end, he puts a comment in. It began to end when Guglielmo Marconi sent radio signals across the Atlantic in 1901, which heralded a new era of technology that later gave rise to computers and overcoming the limitations of our minds. Marconi started it. It's gradually been developing partly mathematically, partly technically, in all sorts of ways. So Marconi was really in at the beginning. We made many contributions during the years. We established research facilities fairly soon after he moved into New Street. Of course, he established commercial manufacture, introduced cableless communications for shipping, and of course, worldwide communications. What is less known is that he produced direction finding systems for ground and naval forces in World War I, very responsible for the Jutland battle in that respect. And also ground to air and air to ground communications started in World War I. And that developed from telegraphy finally to telephony. And that led, as we were shown last night, into broadcast radio. Later on, broadcast television. And as we approached the 30s and the possibility of another world war, radar came in. And post-war, we got into a whole new post-war industry of electronics. And Marconi was present in all of these. So what do we really mean by electronics? Well, the Baddow Laboratories, which were taken over during the war, became returned to general research. And because of the work that has been done really on radar and allied technologies, we had a complete restoration of broadcast television. That was resumed. The broadcast radio services were starting to expand as other than BBC started to produce. We expanded maritime services, both civil and the military. And a whole new development was that of civilian air traffic control. We carried on providing military systems much enhanced compared to what they'd been during World War. And we began to see the beginning of automation systems. And all of this was really due to the development of computers. Now, what do we mean by computing and how was it developed? Well, it's important to know that there are basically two forms of electronic circuits. The analog version, which is a continuous flow of current at varying levels to show value over time. Now, that did enable us to do a certain amount of calculations in, for example, aircraft bomb sites, but that was for a single purpose. The other type of electronic circuit is a digital circuit. And this has discrete levels in a series manipulated to show value over time. But it does mean that you are slightly divorced from a time constraint. It also enables the same hardware system to be used for multiple purposes. Hence, you could think of being programmable for these purposes. So we begin to hear references to the digital computer, a device for manipulating information, also known as data. Now, there are two basic types of computer that need to be known about. There's the offline or standalone, and that is used for as and when calculations with no real-time constraints. And this is the form where, for example, it was used in Bletchley Park for code breaking, and in peacetime for weather forecasting, timetabling, office, or even homework later on. The second type is the online or real-time computer. Now, this is used to control and perform actions requiring immediate implementation of operations in a process. And an example of that would be the operation of machinery, the provision of ongoing functions, and in our case, mainly for air traffic control and air defense interception systems. Now, having got a computer, you have to tell it what you want it to do. So we have two things to consider. There's the engineering, and this comprises the physical machine. And we know that as the hardware, and that is the part that is manufactured. Telling it what to do, in other words, giving it instructions, is done in the form of a list of commands and parameters. And the machine has what we call an operating system, which enables it to perform these actions. Now, both the operating system and instructions are known as software as opposed to the hardware. And usually they're produced as a series of coded statements. And simply they can be in a machine form, but for ease of use, certainly later on, they were usually done in the form of written English, which the machine then interprets. We were involved in the Baddow Research Division mainly, and the data information group within that designed the analog processing and display technology, in particular what was known as a fixed coil system for displaying radar information. It was supported, of course, by all the other Baddow Research Laboratories, because we were engaged in fundamental material research, mass studies, and all sorts of theoretical and practical applications. There were over 1,000 people working in the Baddow laboratories around this time. We'd come out of the World War, of course, working with glass envelope thermionic valves. But gradually, these were being replaced by what were known as solid state devices, which we'll address later. And the first of these used a germanium transistor, and this triggered the work on what we now call digital subsystems. The such things as counters, storage modules, and a range of gates that enable you to work with the computer. We needed storage, and the very first one was a simple acoustic delay line, but later we produced what was called a ferrite core store, and we'll talk about that a little later. Later on, we moved into using silicon as the material, and this gave a far higher performance, and in fact gradually led to the provision of integrated circuits, which enabled us to get faster and even smaller equipment. And all of this was going on in the Baddow Research Facility. Just a quick look at what we mean by active components. The valve on the left of the diagram is one that you would have been very familiar with during the war. It began to lead into sub-miniature valves, which is the next one along. And then we moved into the solid state devices. The first two you see there are a type of transistor, and the last one on the end is the move beginning towards more integrated circuits. Still individual components, but now in a very much smaller envelope. You can see therefore how size is decreasing rapidly. Now, it's necessary to know just a little bit about the science and engineering of computers, and the main thing is digital versus analog. A digital circuit operates on signals, and they are called bits, and they simply exist simply at two levels. And you can think of these as zeros and ones, or off and on. An analog signal, on the other hand, operates on continuous values, i.e. it's constantly varying over time. This means, of course, that digital circuits do not have an intrinsic time constraint, so can intrinsically operate in faster times. And typically, we're talking about microseconds, the unit of time equal to 1 millionth of a second, And later on, we got as far as nanoseconds, equivalent to 1/1000000000th of a second. And just for comparison, if you were talking standard electrics, an electron in a conductor would travel about 6 inches. And don't forget, you're talking about fractions of the speed of light. The two diagrams at the bottom show the digital signals switching rapidly between the two levels, and of course the analog signal, the traditional sine wave shape, just varying as it goes along. The other thing you need to know is the phrase of decimal and binary. Now, the decimal system is the one that most people are familiar with, working to base 10. Numbers are, as you see at the top of this diagram here, working from 10, 11, 12, etc., right through up to the hundreds. In the binary system, which is the second one, you're working to base 2. And in this case, each digit represents a increasing power of 2. Similarly to the base 10, but now you are talking in powers of 2. And as an example, if you see the binary number 100101, you would convert it to decimal form, as I've shown you here. 1 2 to the 5th, no 2 to the 4th, no 2 to the cubes, 1 2 squared, 1 2 to itself, and 1 2 by itself. If you turn that into the decimal equivalent, you have a 32, no 16s, 1 8, 1 4, 1 2, and 1 1, giving you a total of 37. So you get this equivalent of coming from binary into decimal. Now, this is where the nomenclature starts to come in. Each 0 or 1 is strictly a binary digit, but that got shortened to bit, and that is the word with which most people are familiar. You will also hear us referring to a set of 8 bits as a byte, and a string of bits is a word. Now, just to give you an example, this is an animation. The top line are the powers of 2. The center line is the value that they would represent. And the bottom is showing you the binary count moving along, translating the binary number into the standard decimal number over on the right-hand side. I'll just leave quite a minute to let it go through one cycle so you can see. Now, that would be a word length of 7. Now, that was obviously numbers, but if you're going to communicate with a computer, you will obviously need to use language. And this is where we have a system called encoding. And encoding was simply a method whereby the whole of the English alphabet used numerical references to encode the 128 characters. So you could have printable ones, the digits 0 to 9, lowercase letters, uppercase letters, and the range of punctuation symbols, together with some non-printing control codes. And by convention, you could indicate that the following number in decimal, in binary coming in, was in fact not to be used as a number, but would be translated into a letter. So we are able to handle both figures and letters. Finally, there is the logic device. Now, this is the physical electronic device which enables the switching between the noughts and the ones, the ons and the offs, to be turned into a whole series of logical functions that allowed you to do the calculations and tell the computer what it was you wanted to do, and then it would do it. I'm not going to go into any details of these, it would take too long. To hold the software, which you remember is the instructions for the operating system and for the instructions about the particular job, plus any data that you're going to use for the operation to be used, the computer needs this storage device. Now, these came in various forms, but the most common one that became familiar used magnetic methods. And what you see here is a single plane of a ferrite core story. It has 1024 bits, And to give you some idea of its size, the core spacing is roughly 1 millimeter, about 0.04 of inch. That's each of those individual slanting items you can see on the right-hand picture is a core, and it's threaded through with a multiplicity of wires. And every one of those has to be accurately aligned in the right direction, at the right angle, and connected in the correct way. There is an apocryphal story that these were best made by Portuguese lace makers. As far as they were concerned, apparently the small size was no problem. They just got on with it and made it. So these individual planes were put together in that manner. Each of those effectively represented a bit in a word. So if you wanted a 20-bit machine, you would have 20 of these planes all lined up, each one taking one single bit. So this is why you got a block of storage, as this is sometimes referred to. How were we involved? Well, Marconi had been involved in data handling from the generation of radar data, right from the Second World War onwards. And we worked with major government establishments as we'd established during the war. And 3 are shown there. But in about 1949, Dr. Eastwood, then the director of the laboratories, who had been an RAF officer in radar, persuaded through a study and implementation contracts 2 systems for VAST and ROTA, which were projects to completely re-establish the UCAR radar defense system post-war. In addition to this, which was the military side, civil air traffic control was beginning to be used quite a lot and required control systems, and in particular, to use data provided what became known as a secondary radar system, which was actually a derivative of the IFF, Identification Friend or Foe, system that had come out during the war. We got an opportunity in parallel with the work for the government in a private venture opportunity, and private ventures in Marconi terms means something that the company takes on without any contract from anybody to start with. It is going to venture its own money. And in 1957, we had an opportunity to supply a completely new system for the Swedish Air Force, and it was completely new. This was known as Strill 60, and it was what they needed to provide fully integrated systems for aerial warfare. It had early warning radar, ground control and interception, and they wanted to do it using computers. They were in the front line of providing compact critical information. Nobody else was doing it quite this way, and they wanted to get ahead of the game. And they were, in fact, the first in the world to provide this sort of service. And they actually wanted to work with us to design it. We did not get a specification from them. We and they combined, so it was a really marvelous product to get working on and start work, in fact, on computer systems, and that's what we did. The project involved the development of a complete computer processor together with peripheral devices. From this, incidentally, we did get a spin-off because, of course, Marconi had actually been part of the Inks Electric Group since 1946, and they already had work going on in the computing side in the process control areas. So we did stay in communication with them. So this is how Marconi's first computer, Transistorised Automatic Computer, or known as TAC, came into being. It was a fast general purpose machine for real-time applications. Remember the distinction between offline and online. For Ferranti, we had to produce 3 of these machines, and they did control data and driving display systems. In addition, because we were working through the English Electric Company, we had 2 machines put in at Wilford Head Nuclear Power Station. And these went in 1966. And they provided the continuous service non-stop from 1968 until 2004, never switched off. Now, as far as we've been able to establish, this would make it the longest running computer in the world. And so far, nobody has disputed that. One of these machines is now in the National Museum of Computing at Plessey Park, which you can go and see, and it has in fact been restored. The other is in a private collection in Yorkshire. Now, from the records we've been able to locate from the historical material, we reckon that there were 7 TACs produced altogether. Technically, it was a fairly standard machine. It was fitted with a magnetic drum storage device as opposed to ferrite core, display screens, and Freedom Flexowriter electronic typewriters. It was 4,096 20-bit words of core store. It worked in 16 microseconds, and it used paper tape for program loading. And unusually, for those who know about computers already, it was microcoded with a very complex instruction set. I mentioned the Flexowriter and the punch paper tape because it is neat to know how we actually got the operating system and the program into the machine. Now, the Flexowriter was already in existence. It is derived really from telex machines. It's effectively an electric typewriter with on one side a reader for reading paper tape, and on the other side a punch for creating paper tape. If you look at the picture to the right, that on the left of it is a 5-hole tape, which is derived straightly from teletext machines. And on the right, you have the 8-hole, which is more common usage in computers. If you remember, 8 bits we were using as a byte. Now, this was the early method of loading into the hardware storage, the ferrite core store. First, the operating system, which told the machine what to do, then a specific set of instructions for the application, and then the value and type of items of data being handled. And the representation, if you remember, we want a whole and for a naught, and a 1 for a top hole. So you were able to provide a digital signal. The later machines that we had did use a magnetic and electronic media, but very many times it was the tape. Interestingly enough, if you think in terms of a roll of paper tape costing perhaps a few shillings in the coinage of those days, if you then removed about 25% of it by punching holes in, it could actually become worth hundreds, if not thousands of pounds, simply because it had become a program. So how did TAC come about? This is in fact the machine. It was no small machine. Over on the left-hand side of the picture, you see 4 7-foot ranks. And individually in those, you can see rows of what in fact are plug-in circuit boards, an example of which is shown on the right-hand side of the picture. Each of the little groups, you can see 6 of them with a transistor end, and the diodes to the left-hand side formed one of those logic gates to which I referred earlier. In fact, there were 6 3-input gates, and it used the form of what was called DTL, diode transistor logic, and it used the microalloy germanium transistors. Now, for this, remember, it was a completely new system. Marconi had to do all the original engineering work on rack design. The printed circuit boards were brand new. Instead of wiring on chassis, we had to do all the design, production, connectors, and cabling. It was quite a major change in approach. One of the things we also had to provide to the Swedish system were the peripherals. We had now to have keyboards and positioning controls. We had specialized radar display systems, because it was effectively a radar system. But in addition, we produced the first electronic tabular display system, which incidentally we also sold to EE for use in their control systems. Now, this was a method of communicating with the computer. And this is what it looked like. I'll give you a moment or two to read this. These characters, as it says, are being produced. They were photographed live from the face of a cathode ray tube. So the computer can now communicate with you in English. I have at this point to declare an interest because, in fact, this was my contribution to the system. I did the design work for the tube system, the actual display, and the generation of the characters. In those days, as you can see, you could see the equipment that you were working on and a heck of a lot more wiring around than you see today. So it was quite good fun. If you want to see an example of this, because we not only eventually sold it to the Swedes, we started to incorporate it in the UK systems as well. This is the Cold War room at Neatishead Radar Museum in Norfolk. And if you get a chance, do go and see it. It is extremely interesting. You can see in the row of consoles at the front, the tabular display on one side and the cathode ray tube of the radar display on the desk next to it. At the front there are all the tote control boards. And of course, behind all of this were rooms full of racks actually driving this equipment. It is well worth going to see. Having got cut our teeth on TAC, the people in the research unit, of course, are still carrying on looking. And they started with some more experiments in high-speed logical design and high-speed ferrite core storage, somewhat better than what we already had. The design team, rather cheekily, called it their high-speed miniature processor, hence it's known as IMP. Now, they were just doing experimental work on logic and ferrite core storage as far as the organization was concerned. But what they actually decided to do was put the two together. And so they produced effectively another little computer. Now, to a rather surprised management at one point, they actually revealed this. And having taken a gulp and a rapid thought, it was decided that really we should have a production machine based on this new machine, incorporating the lessons that have been learned. Now, this did involve designing a completely new set of circuit elements, boards and mounting systems, power supplies and housing. So it wasn't a trivial move. This is what the people came up with. We've now got effectively a desk. And in that desk are rows and rows of logic units with a control panel on top. Incidentally, this machine still exists. It's somewhere in the Science Museum store. We have had them track it down and it is still there. Now, on the right-hand side, you can see what the circuitry now look like. Instead of the individual units on a printed circuit board, they are now encapsulated into this one container that you could see at the top. Now, you then accumulated 8 of those on the small subboard, and 12 of those were assembled onto a main board, which is why we were able to reduce those set of 7-foot racks down to a unit that fitted inside the desk. The production model came out looking somewhat better, and the Myriad 1, as it became known, was built into a desk with battery-powered backup, and it was for our real-time applications, particularly ATC and military, and it could actually be used now in a Convoy, which was transportable. This shows the rear of the desk, and you can see there the boards plugged in. So everything that you previously saw in the 7-foot racks of TAC are now in the back of this desk. And this was the Myriad machine. It had considerable advantages over TAC. A much reduced complexity of circuit gave us a far higher speed because you were working over less distances. It was far faster than other commercially available machines. For those who know, it ran asynchronously, not with a clock. And the intrinsic high speed of the logic made obsolete a few tricks and things that have been used to speed up basically slower machines. Simplification has obviously led to smaller size, much greater reliability, and therefore a reduced cost. It's 6 foot by 3 foot by 2 foot 5, meeting stringent military requirements in that sort of size. The technical details are that we now moved to silicon semiconductors and resistors in what were called TO5 cans. Those were the containers you saw. The connections were thermocompression rather than soldered, and this gave a far higher reliability. Speed had increased with very high speed. The stage delay of one of the logic modules was 8 nanoseconds. And the input output was now 6 to 8 microseconds. You talk to it in a basic language of user code, but we are now moving into what we call high-level languages, and 2 were Algol and Coral, and these are the ones that are really in the form of English, as I mentioned earlier. The design also incorporated a new method of connecting peripherals called a highway, and this machine was capable of handling over 100 peripherals on the highway. Its applications were now many air defense systems, following on from the ones we'd done for the Swedes. It also got taken up and run the Cambridge Radio Telescope system. The gentleman who ran it came along and saw some work that we were doing on the large-scale aerials, which he wanted for Cambridge. He found out about the computer as well and said, could you not use that to control it? And so we designed a complete radio telescope control system. Central Electricity Research Laboratories wanted the high-speed machine to do trials and tests on the way they ran systems. And in particular, on the civil side, the West Drayton flight plan processing system was used to control the flight plan, that is the method of instructing the aircraft routes for the whole of the UK airspace. Marconi Communication Systems, the other arm of Marconi, were working on message switch systems, and they wanted to move into computing methods, so they in fact also absorbed the Myriad. And there were other people wanting to do experiments now on road traffic control. Now, at this point in time, a reorganization of the company occurred, and 2 new product divisions were produced, one called computer and one automation. They did survive for a while, but they were in fact later absorbed back. But this is how we expanded away from purely military and civil ATC systems. For those, I think this might produce a sigh of relief. Marconi's familiar radar systems. On here you see one of our most successful products, the Marconi S600 Convoy. You see here a height finder with its transmitter cabin, a surveillance radar with its transmitter cabin, and on the extreme left, in that cabin were a set of displays and a Myriad computer. So we have now got a complete mobile system able to do all of the work that effectively had been done by the big ground-based system. Now, Myriad 1 was a success, and other people looked at it and decided they would use it, but they didn't necessarily want the compactness or the full range. So we had another look at it, and we designed a modular rack-mounted basis, so you could put together the parts that you want when and where you wanted them. And that meant that we could mount a slightly different machine with a basic configuration that could be extended or whatever. And it turned into 2 cabinets now containing the central processing unit, the CPU, and the other looked after the storage. And the whole was controlled from a desk, and it's shown here. Instead of the complete desk unit, this was a much more convenient method for some people who wanted to use the slightly different route. Typical application of this was we sold one to the NHS Royal Hospital for doing heart rhythm monitoring. They were beginning to move into medical monitoring. A steel production system at Port Talbot Works. London Transport decided to control, for some reason, although we never quite found out, but just the number 11 bus route. And GLC wanted to control London traffic lights in West Central London, so they bought one. And the Defence Communications Centre product took one for message switching. And we also built an in-house bureau, because by now work was beginning to build up on the software that was required for all of these applications. That was a good success. It was decided we could carry on with this, and Myriad 3 was contemplated, and technology had advanced, so we decided to move on a shade more and build this as a modular machine on rack mounting. Unfortunately, circumstances, which we'll cover in a little while, meant that although this machine was conceived and prototypes were made, it was never offered for customer service. It was a much more complex machine, divided up, as I said, into modules. It had a central processing unit. We had an operator's control system. We had a programmer's engineer's control system, and the master peripheral unit, which enabled us to use this same highway type of construction and couple it up to a very large number of peripheral devices. It would have been a very successful machine. We did, in fact, build an in-house bureau using it, and RRE did take it for evaluation, so it would have had quite a lot of usage. Now, from our records that we managed to locate today for that, again, we produced 58 of the various types of Myriad to add to the TACs that we had already sold. Now, just was up to date. The row at the back shows the valve chassis of the type that were used, many more than you'd have seen there in one machine. The center row is that of the circuit boards you saw in TAC, and sitting at the center is the equivalent Myriad board. So you can see how already we are shrinking the whole system down. Things are getting smaller and smaller and faster, partly because of the reduction in size and partly because of the change of technologies. Now, it's important at this point to see where Marconi fitted in and why, in fact, Marconi, as a manufacturer of computers, hasn't really sort of been in the limelight. Over on the left, you can see we start with Lyons, who produced the Leo computers, and they worked again with English Electric Leo, and we had the English Electric Leo computer systems. At the bottom, you can see the National Physical Laboratory at Teddington, and they were a technical partner of English Electric, and they assisted in producing the LACE, DUCE, and KDF9 and KDF8 machines. So English Electric was already into this. Now, in the middle there, you will see Marconi computers at Chelmsford with our TAC and our Myriad, a cancel machine, which was called Myriad, which was called Mentor, and our Myriad machines, and the one at the bottom, which we'll get round to in a minute, Locus. Now, they all combined, and in 1964, we produced this hybrid company called English Electric Leo Marconi Kidsgrow. Now, this also had coupling across to the RCA computers. RCA, remember, in fact, was derived from Marconi America when it was nationalized, so to speak. So English Electric, through Marconi, had a tie-up with RCA, who also produced computers. So there was a tie-up there. You'll see also a line coming in from English Electric Kidsgrove, which had been the National Physical Laboratory builder of their machines. English Electric, Marconi, and the others, plus another group called International Computers and Tabulators, ICT, were combined together in 1968 to form International Computers Limited. Coming into that mix was also now GEC, who had already absorbed Elliott Automation, and they came in, and so you finished up with International Computers Limited. Now, as you can see, it's quite a complicated arrangement. Now, this was a rationalization carried out by Tony Benn, who wanted to form what became ICL, and it was made up primarily from the commercial computer sector. The real-time and military-type machines, such as those from ourselves, Marconi, Elliott, and eventually Plessey, were left out of this new company. So we were sort of sidelined in that sense into it. So we never really got into the limelight. It's just as well in a way, because, of course, International Computers eventually got into the tie-ups with STC, and in the end resulted in a complete crash of what had become quite a good English or UK computing system. We, however, were able to carry on more or less unmolested. Now, following all this reorganization, it became obvious to those of us in the radar side that the Marconi Computer Systems Limited computers would just not provide a sensible basis for our radar projects. They just couldn't hack it. As it happened, at this point in time, really silicon integrated circuits were becoming available, which were the next level in technology. These packing the complete circuit elements now into a single chip, first of all for memory and then for the arithmetic functions. One of our engineers, who was extremely clued up, saw how we could now start thinking in terms of an intelligent terminal, which triggered the design of a whole new system as far as we were concerned, which was called Locus 16, which you remember I pointed out on the previous diagram. Now, in this, we had a printed circuit backplane to provide communication between computer, memory, display drivers, and all the other devices, each housed on a smaller printed board, which was plugged into the backplane. So you could build an intelligent terminal using the necessary devices as you wanted. Moreover, in time, the integrated circuits became increasingly more powerful. You could get more storage capacity, more elaborate processing, and you could modernize the whole product of the machine, but not necessarily without altering things very much. So we got away from this complete re-engineering design problem. This, in fact, is a Locus 16 board. This is now everything you previously saw on the rows of boards in the previous machines. So we've now got it down to a single board. All of that, which had been in 7 racks, had been in a big desk, had been in the much smaller desk, now disappeared into effectively 1 rack. Each of those units now, which you can see plugged in along, was effectively almost a complete computer within itself, and you could have as many of these as you wanted in a rack. This was the earliest model that we made. And it was a 16-bit machine, had 2,000 words of 16-bit memory. It had all these processors. It had also a display processor for driving the displays, serial links, and it could also do its own diagnostics. And we had a method of allocating storage in a far better way. That was the Locus system to start with initially. As the development of research progressed, we increased what went into the Locus system by an enormous amount. We added more processors, we added different methods of doing things. We even went to a multiprocessor operating system, which we can do time sharing, memory management, database management, everything all combined into one unit. And this, in fact, finished up looking like this, which, as you can see, is virtually the same as the initial model. All that happens is that inside each of those plug-in modules, we have more and more complex circuits. Just to give you an idea of what we could do now with a Locus, this, in fact, as you can see in the center, has the Locus bus. That is the backplane into which everything plugs. And all of these different types of processor could be plugged in using those racks. And at the top, you will see there are 3 types of display that we've shown: the interactive tabular, a graphics display, and the tote tabular display, all being driven from the controllers inside. We even had at the bottom, as you can see now, voice communication systems built in to what previously had been just a computer system. If you now remember the layout of that diagram, this is what it actually looked like. The whole computer and display system has now gone into one console. This is, in fact, for one of our major products, which is the Improved UK Air Defence Ground Environment, or IUCAG. And again, you could see one of these if you go to Neatishead. They do have one on display there. This is the rear of the machine, and you can see Locus devices into the shelf at the back. So the whole thing is now reduced back again, down effectively to a desk, but far more powerful than the previous. This system, which is effectively a complete environment workstation, allowed us to effectively produce a variety of role-dependent systems. The way we were able to do this was we had software control processors, which gave us great flexibility. And this was a major advance in cost-effective components for C3I, control, command, and communications, because we could implement a very large multi-level system with workstations identical from the hardware and software. You could detail the function for a particular role determined by tables generated in software, stored in the system, and loaded in when you need to. So any user could, in fact, change the characteristics of his particular workstation to meet needs as they evolved. That was in the military service. The civil side also became very interested, and this is in fact the Scottish Air Traffic Control Centre. As you can see, we're now working not like the old radar days in darkened rooms. You're now in fully lit areas. SCATSI was built in 1974 and contracted by UK CAA with the company for a completely new system at Prestwick. And it controlled the air traffic in the whole in the UK. We are over 30 PPI display systems, each fed by one locus engineered system. And it monitored all the aircraft in 2 million cubic miles of airspace above Scotland. It was a very powerful system, but even so, it was much extended in the 1980s with more locus systems added. So it was a very successful system. So far, we've really talked about hardware, but you must remember that we needed this method of telling the machine what to do, which was the software. And running through a sort of timeline, TAC and Myriad was initially performed, the programming was performed by the hardware engineers. They were the people who built it and designed it, and therefore knew what to do with it. As we progressed, we actually recruited dedicated programmers. Mainly were all graduates, and the initial projects were still developed fairly informally. Like the two sets of engineers got together and decided what was needed. But as the systems became more and more complex, we had to do a lot more disciplined development. And this really culminated in the 1970s for the flight plan processing system that we mentioned earlier. But even that, by the late 70s, was inadequate to handle it. And we had to go to a much more sophisticated set. We generated this functional definition language to formalize requirements. And at that point, programming became software engineering. We actually started to employ the same disciplines on the software as we employed on the design of hardware. We also developed a range of development tools to support procedures being able to give rigid control. And the company actually helped the government with real-time policy. And we also took quality management procedures and extended them to include specialist software quality engineers. So the whole system gradually evolved into a very coordinated system. We were also learning a great deal about the whole system software development process. And as you probably know, many other systems over the years have had great trouble with their software. And we culminated with the IUCAD work for the machine I've just talked about, carefully partitioning things into packages, and then subsequent stage build-up of subsystems and the production of ego-less reviews. In other words, everybody had to agree with everybody else about which way we wanted to proceed. Now, to do this, we moved from software produced by very few software wizards. It was regarded as a bit of a black art in the first place. And to do these very large systems, we actually had dozens of softies, as they became known, usually split into several teams. And that meant we had coordination problems. It didn't matter what we did this, there's nothing could be infallible. And as we've remarked, there were such problems probably hidden in the TAC Intercept program from all those years ago. But all we can say is that TAC delivered that service in whatever form for approaching 40 years with no problem, so we weren't too worried. Nevertheless, through all of this work, our software engineering capability was far superior to many major players that we knew existed. Now we come around again to company policy. Mexel, which is the company organization we previously talked about, expressed no interest whatsoever in Locus 16. Unfortunately, this was a lost opportunity because backplane technology, which we had devised, was also introduced, not surprisingly, by other people, in particular DEC, at about the same time. And then it became universal almost to everybody, particularly in the IBM personal computer. Now, it would have taken a substantial marketing investment, but it could have been a major business. But the potential wasn't recognized by management, who by that time were going off in entirely different directions, which resulted in the ultimate problems. And for that reason, the Marconi capability in computing never went any further. It was never fully developed. But on our radar side, Locus became the mainstay of the business. And from records that we've again accumulated, we think we have a total of over 500 Locus installations delivered. So you now have an estimated total of Marconi computers to approaching 600. And we don't think that by any stretch of the imagination or calculation, that is a very poor number. We think we did become a major player. Now, just as a little bit of interest on the side, while I was putting this lecture together, I was talking to various of our colleague engineers, and these are a couple of remarks that came up. It just showed where we were. The recent lecture on car electronics, that the chip in each door handle on a modern car used 32K, that's 32,000 words of storage. I, this is the engineer, pointed out that we used to get the software for a complete air defense system into this amount of store, including tracking aircraft performance, data and display management. The lecturer also stated that some cars now had more lines of code than the Typhoon fighter. So things must now be very sophisticated or code very inefficient. And he said, I suspect the latter. Think about that what you will. Just to summarize where we were in the Marconi environment, Marconi was an experimenter. He did get a Nobel Prize for physics, but he was essentially an engineer, an experimenter rather than a theorist. Initially, he built and used equipment based on practical approaches. He did push it to the limit and beyond. Later, of course, theory caught up and justified his approach, and he and his colleagues established research units on a much more standard basis. But I think it can fairly be said that Marconi, the engineer, his scientific, engineering, and manufacturing staff observed the accolades that were given to them by Lovelock at the beginning. Also, as a company, it was the first to institute training for both technical staff and factory. And this was highly regarded and still is even today. So we think it is a sad day when probably the most disgraceful example of stupidity and mismanagement in the history of British business affairs resulted in its complete failure in 2001. And that brought to the end our record of technical innovation and exploitation, and nowhere else came anywhere near it. I prepared this slide over the beginning of this year, and of course, since the COVID-19, and that we now have to think about the future in a slightly different way. And so I wrote this slide since the onset of the worldwide imposition of lockdowns and quarantines, during which we are experiencing now what was almost certainly a new world order, using wide-scale online communications in both business and home environments. Now, how do we actually manage to complete this centenary program? There were other lectures due to be delivered, and we would have covered the Internet of Things, IoT, and another group of applications using artificial intelligence, both of which, if you remember, were referred to in my opening remarks. There is, in fact, a remnant of the Baddow Research Centre still around in the form of the BAE Applied Intelligence Laboratories, but really it's more representable even more that with a demonstrated capability, design and supply our large-scale systems that we did, there will not be a Marconi presence to lead the UK into the forefront of our era of the Nova scene, which sprang from Marconi's original vision and practical approach. If I may now, I'd just like to give an epitaph. I started with a quotation from a book, and I'd like to finish with one. The essence of the Marconi approach was centered on its people, starting with Guglielmo Marconi himself and the staff he gathered around him. And we all know to be known as a Marconi man or woman was to be acknowledged as personally belonging to a rather special family business. And it was a family business. We have plenty of examples of sons and daughters following their father and even their grandfathers into the business. A very interesting quote comes out from a book published at the end of the war, Marconi 1935 to 45, for war record. And this quote is included in it. And I would just like to read it out. A research engineer walking in the soft sunshine on the little lawn beside Marconi College and looking back over the feverish years, the war years, of course, now closed, was trying to explain this thing, the manner of tackling the scale of scientific and manufacturing work undertaken by the company. He paused, considered for a moment, and then said, as one who states an objective scientific fact, it is, I think, that the Marconi company has a soul. So truly now, unfortunately, we are going to live in a world without Marconi. Thank you for listening.